In this module, we will look at data types in Java.
The objective is to learn about the categories of data types and understand the primitive data types in detail. Data types in Java can be characterized into primitives and non-primitives. Primitives are Boolean, char, byte, short, int, long, float, and double, while non-primitives like class and interface, which will be covered in detail later. Let's look at the primitive data types in Java. Primitive types represent single values, not complex objects. There are 8 primitive types of data, which are byte, short, int, long, char, float, double, and boolean. These can be put into 4 groups. Integers, which comprise of byte, short, int, and long. These are used to represent whole valued signed numbers. Floating point comprise of float and double. They're used to represent real numbers, numbers with fractional precision. Characters just has one type, char, which represents symbols in a character set like letters and numbers. Boolean again just has one type, and it's a special type for representing true and false values. Let's look at integers in detail. Integers comprise of these 4 types, byte, short, int, and long. It is used to represent whole numbers. Byte represent signed numbers, both positive and negative. It is the smallest type of integer. The width is 8 bits, which determines the range, which is from -128 to 127. It is useful when working with data which is in the form of byte, that is reading or writing data from files. And it has a declaration as shown below. It says byte followed by a space followed by a number. Short. Short again can represent signed numbers, both positive and negative numbers. It has a width of 16 bits, which results in a range of minus 32,768 to 32,767. It is rarely used. It has a declaration form as shown below, which has short space number. Next is int, can represent signed numbers, both the positive and negative numbers. Width of 32 bits, which produces this range of -2147483,648 to 2147483,647. It is very commonly used data type. Variables of type int are most commonly used as loop control variables, as we have seen, and also to index arrays, which we will see later. It has a general declaration form as shown below, int, space, and the identifier, in this case number. Long, again used to represent signed numbers, both the positive and negative numbers. It has a width of 64 bits, which produces a huge range. So it is used to hold very large values. It's used where an int type is not large enough to hold the desired value. It has the declaration as shown below, long, space, identifier, in this case number. Here's an example program which uses the integer data type. So we have light speed variable of type int, days variable of type int, seconds variable is of type long because the product of days multiplied by 24 into 60 results in a value which is beyond the range that a int can hold. Similarly, distance is of type long, which contains the value of light speed multiplied by seconds, which again produces a value which is beyond the range of an int type. So this program produces output as shown below. In 1000 days, light will travel about 160,704,000,000,000 miles. So pretty big number that is beyond the range of int. So how are these integer types stored in memory? So all integer types are represented by binary numbers. Here's an example to see how a decimal value is converted into binary form, and then from the binary form, how can we get back the decimal value? So the binary representation of a number, in this case, we have chosen byte B is equal to 42. In terms of binary bits, On the right side, this is how we have converted it into a binary representation. So 42 is nothing but 1 0 1 0 1 0. So if we put it in the place value chart with their corresponding place names, since it is a byte, so it has 8 bits. So we started from 2 to the power of 0, 2 to the power of 1, it goes on till 2 to the power of 7, and the numbers are placed from right to left, where the rightmost bit is placed under 2 to the power of 0, and this continues till 2 to the power of 7. So if we have to convert this binary back into the decimal form, the value of 2 to the power of n is multiplied by the bit, and then the result is the that product of each of these bits is summed up to get back the decimal value. So in this case, 1 is multiplied by 2 to the power of 5, which is 32, plus 2 to the power of 3 is multiplied by 1, which is 8. 2 to the power of 1, which is multiplied by 1, the product is 2. So we have 32 plus 8 plus 2, which results in 42. So the obvious question is, are both positive and negative integer types represented in the same way? Yes, in terms of representing them in binary form, but there's a slight difference in the way negative numbers are represented. Negative numbers are encoded using 2's complement. Now, what is 2's complement of a binary number? Let's check this with an example. Let's see how to represent minus 42 in 2's complement. So first, the number 42 is converted into the binary form. As we have seen previously, it is 00, 10, 1010. Then a ones complement of that number is taken. Ones complement is simply converting the zeros to ones and ones to zeros. So in this case, this 0 is converted into 1, this 0 is converted into 1 is converted into 0, 0 is converted into 1 is converted into 0, and so on. And 2's complement is adding 1 to the 1's complement. So here 1 is added to the 1's complement, which results in this output, which is 11010110. So this is the 2's complement of minus 42. So that was encoding into 2's complement. Now how can we decode the 2's complement number to its original value? So we can just simply reverse the steps. The representation that we would have is the 2's complement. The most significant bit specifies the sign. If it is 0, it is positive number. If it is 1, it is a negative number. So we can take the 1's complement of this number, where we simply convert 1's to zeros and zeros to 1's. So we have this is the 1's complement, and then just add 1 to it. So once we add 1 to the 1's complement, we get this representation, which is 0 0 1 0 1 0 1 0. So if we take the product of their place names with the value, we get 32 plus 8 plus 2, which is 42, and the most significant bit is 1, so it is minus, so it is minus 42. Now why 2's complement encoding is used? 2's complement encoding is used to represent negative numbers, as we have seen, and this helps us avoid the issue of zero crossing. Let's see this with an example. We'll consider binary form of byte B, which is assigned a value of 0. 0 is represented as 0 0 0 0 0 0 0 0. Pretty straightforward. So if we convert this into the ones complement, we get all ones. Now if ones complement would have been used, so to get back the original value, we had to convert this ones complement back to basically take the ones complement of this representation, which would result in all zeros, and the most significant bit, which would be 1, would be used to represent the sign. So in this case, this would result a positive 0 represented in ones complement, and then converted back into the original value would result in minus 0. Minus 0 is invalid integer in math. Hence, if we use 2's complement, it results in a zero crossing, wherein let's consider this again, starting with the binary representation of 0, which is all zeros. Then we take the ones complement, which will result in all ones. Then 2's complement is achieved by adding 1 to the ones complement, which will result in all zeros followed by 1. And since this is a byte, so this 1 is of no significance, and the value that we get back is all zeros. Hence, when we try to decode it back to its original value, we take this representation, which is the 2's complement, we take one's complement of it and add 1 to it, which will result in zeros, and then the most significant bit would be 0, which will result in a plus 0, which is a valid integer. Hence, 2's complement encoding is used to represent negative numbers. Next, let's look at floating point data type. The floating point data type, as we have seen, comprises of float and double. So this data type is used to represent real numbers. And Java adheres to the IEEE 754/1985 floating point standard. This standard defines the format of 32-bit and 64-bit floating point numbers. So these numbers are used in evaluation of expressions which need fractional precision. Examples of floating point numbers are 19.95 and 3.1415. So characteristics of floating point: float can be used to represent sign numbers, both positive and negative. It represents a numeric value using single precision. Single precision is 32-bit representation of that number. So 32 bits, so obviously the width would be 32 bits, which results in this range, and is used to represent currency in most of the cases. Declaration is as below: float space identifier, in this case temperature, and this is how it is represented. So 32 bits, the most significant bit is the sign, the next 8 bits represent the exponent, and the next remaining 23 bits represent the fraction. In terms of double, again can be used to represent sign numbers, both the positive and negative. It represents a numeric value using double precision. Double precision is the 64-bit representation of that number. Obviously the width is 64 bits, which results in this range. It is used to hold values of functions like sine, cos, etc. Declaration is of the below form: double space identifier, in this case area. So the most significant bit is the sign bit, followed by 11 bits of exponent and 52 bits of fraction. So an example, we have radius, which is of type float. Pi is of type double. So the product of pi into radius is assigned to a, which is of type double. You just note that the declaration for radius, the value of radius is 10.8 f. So f indicates it is floating point, not a double literal. And the output of the program is shown below. Area of circle is 366.43623, and so on. So let's see how floating point numbers are represented. So there are three elements, as we have seen in a floating point representation: sign, exponent, and mantissa, or the fraction. Sign is the most significant bit of the binary representation. 1 implies a negative number, while 0 implies a positive number. Exponent, the next 8 bits of the binary representation. So 127 number is the bias for 32-bit floating point representations. So the bias is added to exponent number to produce exponent bits when converting into floating point representation, and the exponent bits decimal value is obtained, and the bias is subtracted to obtain the exponent number. So bias is 2 to the power of n minus 1 minus 1, and the fraction, which is the mantissa, the next 23 bits of the binary representation. It consists of 1 and the fractional part. So let's see how to convert to a floating point representation. So let's convert minus 17.35 into 32-bit floating point representation. So here, since it is a negative number, so the sign bit will be 1. Next, exponent. So how do we derive it? We'll find the nearest smallest number to 17.35, which can be expressed in the form 2 to the power of n. So 16, which is very close to 17.35, can be represented as 2 raised to 4. Hence the exponent will be 4. Since the bias for 32-bit representation is 127, we will add 4 to this bias to obtain 131, which will be represented in binary representation as 10000011. Next, mantissa. So 17.35 is in binary is 10001.01011. So we need to move the binary point so that there is only one bit on the left of the point. Adjust the exponent of 2 so that the value does not change. This is normalizing the number. So 10001.01011 in normalized form is 1.000101011 into 2 raised to 4. Now consider the fractional part and represent it as 23 bits by adding zeros. So from this, we just take the fractional part after the decimal point, which is 000101011, and add zeros to make it a 23 bits. Thus the floating point representation of minus 17.35 is the sign bit, which was 1, exponent bits, followed by the fraction bits. Now let's see how to convert this floating point representation into the decimal representation or the decimal number back. So to convert this number, the first bit is the sign bit. This indicates, since it is 1, it indicates a negative number. Next, exponent. Now, if we take this next 8 bits and subtract the bias, so the next 8 bit is 10000011, which is 131, and we subtract the bias, which is 127. We get back 4, so the exponent is 4. And mantissa, as we had seen, we had ignored the 1 and we had just taken the fractional part. So it is implied that it has to be 1 plus fractional part. So the fractional part from the remaining bits, which is the sign bit and the exponent bit, are already considered. Now the remaining 23 bits are the mantissa or the fractional part bits. So those are converted into their decimal representation as seen here. And we arrive at this value, which is 0.083984375, and it continues. Thus the mantissa is 1 plus this decimal number, which is 1.083984375. Hence the decimal number is as given below. So it is sign into exponent into mantissa. So since the sign is minus, it's 1, so we take minus 1 in raised to 1 into 2 raised to 4 into the mantissa, which is 1.083984375. So again, minus 1 raised to 1 is minus 1 into 2 raised to 4 is 16 into 1.083984375 results in 17.35. Next, let's look at character. So it just has one data type, which is char. It is used to store the characters. So Java uses Unicode to represent characters. Unicode is a type of encoding and is a unification of dozens of character sets such as Latin, Greek, Arabic, Cyrillic, Hebrew, Katakana, Hangul, and many more. So it requires 16 bits. The range is 0 to 65,536. There are no negative values. A char can be declared as shown below. Char space identifier, in this case letter. An example shows that a value of x is assigned to letter which is of type char. Note that the character capital X is within the single quotes. You can also assign the alphabet's ASCII code as shown below. So in this case 88 is assigned to letter of type char. So 88 is nothing but an ASCII code which represents capital X. So a note on ASCII: in ASCII representation, each character or number is represented by a number. The numbers from 0 to 9, uppercase and lowercase English letters from A to Z, and some special characters have their equivalent ASCII number. For instance, 65 is used to represent capital A, 97 is used to represent small a, 95 is used to represent underscore. So when 88 is assigned to letter of type char and the value is printed, so the output of the print statement would be capital X. Although char holds a Unicode value, you can treat it as an integer and perform arithmetic operations on it. That is, we can apply increment operator to above letter, letter plus plus. So in this case, the value of letter will be 89, and on the console output, it will print as Y, because 89 is an ASCII code for capital Y. Here's an example which uses char variables of type char. Here ch1 is of type char, which is assigned a value of 88, and ch2 is of type char, which is assigned capital Y. So when we print, we see ch1 and ch2 is X and Y respectively. And if you increment ch1, it results in Y. ch1 now is Y. Next is Boolean. It's a primitive type to represent logical values, true or false. So this is the type returned by all relational operators, as in the case of X less than Y. This is also the type required by conditional expressions that govern the control statements, such as if and for. An example for Boolean. So in this example, B is of type Boolean, which is assigned the value of false, and its value is changed after the print statement to true. So B can be used as the condition in the if control statement, as we see here. So three things to notice in this program. True or false is displayed when Boolean value is output using println. The value of Boolean variable is sufficient to control the if statement. There is no need to write B is equal to true. The outcome of a relational operator such as less than is a Boolean value. That is why the expression 10 greater than 9 displays the value true. So to summarize, we have learned about integers, floating point numbers, character, and Boolean groups of data types. The different types of integers, which are the byte, short, int, and long, and the types of floating point numbers, which are float and double. How integers and floating point numbers are stored as bits, and characters are represented using Unicode, which is a superset of ASCII. Boolean values are used in conditional expressions.